I would like to welcome Dr. Fabrizio Sebastiani from CNR in Italy, that he is going to talk about a very interesting topic, namely the prediction of classifier accuracy in the wild. So I welcome you, Fabrizio. The floor is yours.
Thank you very much. So thank you all for attending this talk. Good afternoon to everybody, or let's say good evening or good morning, depending on what area of the world you are in. So let me introduce this talk. Okay, so as the title says, I will talk about a task predicting the accuracy that our classifier is going to have, a task that is probably going to be interesting for many of us. And what does in the wild mean? It means predicting the accuracy that our classifier is going to have on, let's say, data in the real world. Okay, data that might be distributionally different from the data that we have in our lab and that we have tested our system on. Okay, so let me, let me introduce classifier accuracy prediction. Essentially, this is a task that we normally perform via k-fold cross-validation. No. The problem with k-fold cross-validation is that it returns reliable results only when the training data and the data, the test data, the data we have tested our system on, when these data are IID, identically and independently distributed. Okay? But it's still an open problem when T and U are not IID, a situation which is often described as saying that the unlabeled data are out of distribution, or described as saying that there is dataset shift between the distributions from which T and U have been sampled out. So this is essentially classifier accuracy prediction is one of several tasks that have to do with dataset shift. Among these tasks, there are, say, estimating the type of dataset shift which is present in our data, or estimating the amount of dataset shift, or also adapting our own classifier to shift data, adapting to data that are out of distribution, which is what we often call domain adaptation. Indeed, predicting classifier accuracy in the wild is useful, because it gives an answer to an often stated question. How is my old classifier going to perform on these new data? Old classifier might mean a classifier, for which I don't have the original training data available anymore, or a classifier which I recognize is was trained on data which are pretty different from the ones that I'm going to tackle. So the question is my old classifier good enough? Is it going to be good enough on these new data, or should I obtain new labels from these new data for retraining the classifier? So, of course, this is very important to be able to assess this classifier accuracy on this new data, especially important also for responsible use of AI, because sometimes what we don't want is to deploy our classifier maybe on a high stakes domain, where the classifier is not going to perform as well as we had hoped it to be, So this talk will be in general about predicting classifier accuracy in the wild, and we'll also introduce a method that we have recently developed for doing classifier accuracy prediction under dataset shift, a method that we have called QAC. So let me introduce dataset shift in some detail. Essentially, the notion of dataset shift starts from regarding the joint distribution of our data, which is often, indicated as PXY, where X are the covariates and Y are our labels. And dataset shift is the situation in which we have two distributions, P1XY, which is the source distribution, P2XY, which is the target distribution, so source distribution from which the training data come, and target distribution from which the unlabeled data come. So dataset shift is the situation in which P1 and P2 are different, while the usual situation that we often deal with in our research is the one in which P1 and P2 are the same. So the situation in which the data are independently identically distributed. So what are the causes of dataset shift? There may be multiple causes, but there are, let's say, we can group them in two different causes, depending on whether the shift is in the data that model a certain reality, or whether a shift is in the reality. So real shift is a situation in which there are variations in the environment that the data represents. So the environment that the data represents is not stable, is not stationary. And so the conditions under which we are going to deploy our data are not the same as the conditions under which the classifier was tested. A typical example, say, let's think of September 11. Well, before September 11, if you were looking at newspapers, the prevalence, the proportion of terrorism-related news was very small. It suddenly becomes very high after September 11. So this is a change in the environment that the data represents, real shift. A different type of shift is virtual shift. So virtual shift has to do with the misrepresentation of the environment on the part of our data. So our data don't represent the environment correctly. Our training data don't represent correctly the environment which the classifier is going to tackle once deployed. And the reason is that there may be several causes why we may have introduced in the training data some sample selection bias. So a bias that we may have introduced intentionally, say, when oversampling the minority class. Okay, so suppose we have to train a classifier for recognizing a rare illness, a 1 in a million illness. Okay, so certainly we have to oversample the minority class in order to build reasonable classifiers. But the sample selection bias may have also been introduced unintentionally. Say, if we have used active learning in order to train our classifier, because active learning builds a training set which is anything but a random sample of our distribution. Okay, so active learning inherently builds training sets which are biased. Okay, so let's see how we can tackle dataset shift. The best way to tackle dataset shift is via factorization, by decomposing the prior, let's say, the joint distribution of the covariates and the labels. Okay, so one typical way in which we can do this factorization is to factorize, to decompose pxy as py given x times px. This is a factorization useful in so-called x implies y problems, okay? Because it basically makes it explicit the dependence of y on x. So these are problems which have been referred to as causal learning, problems in which we want to infer the presence of a certain phenomenon, y, from its causes, x. A different factorization is to factorize, to decompose pxy as px given y times py. And this is useful in so-called y implies x problems, because it makes it clear, it makes the dependence, it makes explicit the dependence of the covariates x on the label y. So these are problems which are called anti-causal learning, problems in which we want to infer the presence of a certain phenomena from, not from causes x, but from symptoms x. So depending on whether we are in the presence of causal learning or anti-causal learning, the literature has identified 3 major types of dataset shift. So one is called covariate shift, which typically affects x implies y problems. The other is prior probability shift, which typically affects y implies x problems. And the third one is concept shift, which may affect both types of problems. And I will look at them in detail one by one. So covariate shift. As we said, it affects X implies Y problems. It affects causal learning, in which we infer the presence of a phenomenon X, a phenomenon Y from causes X. So one typical case is weather forecasting or avalanche forecasting. So in avalanche forecasting, we want to foresee whether certain avalanche will fall based on some physical potential causes, such as humidity, presence of wind, presence of high snowpack, etc. In these cases, if we want to learn an avalanche forecasting system, we may incur in covariate shift. Covariate shift is defined as a situation in which the causal dependence between X and Y doesn't change. So P1 of Y given X is the same as P2 Y given X. But the marginal distribution of the covariates changes. So P1 of X is different from P2 of X. So a typical case, suppose I want to do avalanche forecasting. I train my system on data from, say, northern Italy, from the Alps, and I want to deploy my system on Scandinavia, Well, here the physical laws that to which avalanches obey are the same in Scandinavia and the Alps, but the typical conditions that are found in the Alps and in Scandinavia are different. Okay, so this is an example of covariate shift. So prior probability shift is a different one. So the context is Y implies X problems, anti-causal learning. So that is inferring the presence of a phenomenon Y from symptoms, not from causes, In this case, well, examples of these are maybe handwritten digit recognition, authorship attribution, or predicting illnesses from symptoms, okay? So take handwritten digit recognition. So essentially, here, we have a situation in which a person draws, say, a zero, draws a zero and uses some graphical tracts, to generate this zero. So, the class zero implies the covariates, the graphical tracts. So here we might have prior probability shift, might incur in prior probability shift, type of shift which is also called label shift, which is defined as a situation in which the causal relationship between the covariates and the labels stays the same, is invariant across training data and unlabeled data, but the marginal distribution of the labels change, okay? So an example might be digit recognition for binary digits only. We have trained the system to do handwritten digit recognition. We have trained it, to recognize decimal digits from 0 to 1. And now we want to deploy it on a situation in which we have to recognize zeros or ones only. Okay, so here the prevalence, the proportion of the classes has changed, but the way of drawing zeros and ones has not changed. So concept shift is the third type. Okay, so it may affect either X implies Y problems or Y implies X problems. So it's actually defined as a situation in which the causal relationship between covariates and labels changes. Okay, so it might be the case that P Y given X change or PX given Y changes. Okay, so one example of concept shift is, say, in product reviews. Product reviews may be, marked from 1 star to 5 stars. So our perception of what counts as a positive review may change. So maybe in previous data, previously we had an attitude towards considering positive anything that was marked from 3 stars onwards. But then our perception might change, and we decide that we want to consider positive only what is marked from 4 stars upwards. Okay, so this is concept shift. So the very concept of what counts as positive has changed. So let's go back to classifier accuracy prediction. So recently in the literature, there have been a number of classifier accuracy prediction methods which have emerged in the literature in the last 5 years. One of the problems is that the state of the art in this task is still somehow unsatisfactory for 3 reasons. Okay? So first of all, the error that these methods do, is still sometimes too high for these methods to be applicable in practice. And the second reason is that the experimentation which has been carried out in the papers that have presented these methods sometimes is not really thorough enough. And the third reason is that most of the methods that have been presented deal with only one classifier accuracy measure, which is typically vanilla accuracy. So we actually sat down to do some research in order to try and improve on all these 3 problems. And the method that we are going to present, which is called QUAC, has 2 interesting characteristics. First of all, it's independent of the learning algorithm used for training the classifier. So it works for SVMs, it works for deep learning, it works for logistic regression. And the second is that it is independent of the classifier accuracy measure chosen. So at least in theory, it works for vanilla accuracy, F1, balanced accuracy, and the rest. Okay. QUAC is called quantification. It comes from quantification for accuracy prediction. And the reason why I'm speaking of quantification will be apparent in the next slides. So speaking of QUAC, it gives me the opportunity to describe what is the standard experimental setting for classifier accuracy prediction. Typically, we assume a domain X of items, a set of Y of classes, a training set which is assumed unavailable. So we assume that we don't have training data anymore, which may be a realistic assumption. We still assume instead that we have a validation set available. So we have other data coming from the same distribution from which the training data had been sampled. And we have unlabeled data available from a different distribution, P1 different from P2. And it is indeed the accuracy of our classifier trained on T, the accuracy on U that we want to estimate according to an accuracy measure A. Okay. So this setting is essentially equivalent to a setting in which no validation set V is available, but the original training set T is still available. So all the solutions that work for one setting work for the other setting too. So where does our method start from? It starts from the observation. From the observation that any classifier accuracy measure can be computed from a contingency table. The contingency table obtained by applying our classifier H to the unlabeled data. So essentially, if we want to estimate the accuracy of our classifier, we only need to estimate the values, the counts of each cell in the contingency table. It's easier said than done, but we'll give it a try. So the idea that derives from this observation is the following. We want to view the cells of the contingency table as classes. Classes, that may be, the object of classification, okay? So once we see them as classes, what we can do is to train on our labeled validation data a model that estimates the values of these contingency cells, estimates how many of our unlabeled items have ended up in these contingency table cells, which means how many of our unlabeled data belong to these classes. So belonging to a class is a familiar notion. It falls under the domain of classification. So we can foresee that we might want to train a classifier in order to estimate these values. And of course, once we have these estimates, we use them to predict our accuracy value for our classifier. So the key step, of course, of this method is step number 2. How do we train this model? Well, the idea is that we can represent the data points as extended pairs. Okay, I'll call them x double dot and y double dot. Okay, so what is the vector x double dot? It's a vector that contains all of the original covariates, all of the original features, which our classifier H uses, and also contains the posterior probabilities, the confidence values that the classifier has returned for this item, So, what is y double dot, the label? The label this time represents the contingency table cell where this item has ended up, So it's a label that ranges not on the original set of classes y, but on our contingency table, So the story is different for labeled data and unlabeled data. For the data points in our validation set, which are labeled, y double dot encodes a pair. The pair that contains the true class of X, we know it because the validation data are labeled, and the class that H has predicted for it, because we can apply our classifier H to this item and predict a class for it. Okay. So for data points in the unlabeled set, this is different. Y double dot is unknown because we can know the class which is attributed to the item by the classifier, but we don't know the true class. So y double dot has to be estimated. Observation number 2. The observation number 2 is that in order to estimate the values, the counts of the contingency table cells, we don't strictly need to predict the cell where each individual data point will end. We only need to predict the counts, predict the counts or the frequencies, the proportions of data points that will end in each cell. This observation leads to an idea. Instead of using classification, which essentially would tell me the cell where each data point will end, we want to use quantification methods to estimate these frequencies. What are quantification methods? Quantification is a task which is somehow intermediate between classification and regression, and it's the task of training predictors of the fractions of data points that belong to each class, predictions of the relative frequencies of data points, predictions of the prevalence values, you may call them whatever you want, predictions of the fractions of data points that belong to each class. And one interesting aspect of quantification methods is that they tend to train quantifiers which are robust to dataset shift by design, because let's say dataset shift is the main concern which is at the heart of quantification research. The very first paper, of the quantification literature was a paper that tested its system under prior probability shift. So in a sense, dataset shift is, at the heart of quantification research. Well, what is the goal of quantification methods? The goal of the quantification literature is to improve the accuracy in predicting class frequencies over the simplistic technique of classify and count. Classify and count is essentially apply a classifier to all of the individual items and count how many items you have attributed to each class. And to improve over this simplistic method by deploying special purpose machine learning techniques. So machine learning techniques which are specifically oriented to predicting frequencies rather than assigning labels to individual items. So up to now, I've given you a very general picture of QUAC. Essentially, in this talk, I will focus, and in the experiments I'm going to present, we have focused on a specific setting. So the specific setting is predicting the accuracy of binary classifiers. So we leave multi-class classifiers aside for the moment, and also focusing on prior probability shift. So leaving covariance shift and concept shift aside for the moment. So essentially, during the course of this research, we have developed 3 different variants of the Quack method. So the main variant is what we call the 1x4 method. And it's essentially what I have described up to now. So it's a method which is based on training on our labeled validation data, a single quantifier, a multi-class quantifier, because it deals with 4 classes, a quantifier that estimates the frequencies of the 4 classes TP, FN, FP, TN, the 4 cells of the binary contingency table. Okay, so, you know, for the 1x4 method, the basic process is essentially the one I've described up to now. So first of all, we classify the instances of the validation set, the labeled instances of the validation set, using our trained classifier H, so that we can obtain our extended representations X double dot, Y double dot. Okay, so for these instances, we have not only the original features Xi, not only the true class Yi, but we also have the predicted class, you know, and we have all of the posterior probabilities that the classifier has returned, you know. So we also can classify the instances of U, the unlabeled set, using our classifier to obtain extended representations for which we have only X double dot, because we don't have Y double dot, for the simple fact that for the unlabeled data, we don't know the true class. At this point, we can train on V double dot, on the extended representations for the validation data. We can train a quantifier, a multi-class quantifier, that allows us to obtain, you know, estimates of the counts of these 4 classes, estimates of the fractions of unlabeled items that have ended up in the TP cell, estimates of the fractions that have been ended up in the FN cells, etc. Okay. So of course, I mean, this method, which is called the 1x4, admits of a multi-class version, you know, an evident multi-class version, which is called the 1 by n square method, for the fact that, you know, in the multi-class version, we are going to have a contingency table which has n square cells. So we have to train one single multi-class quantifier that deals with n square classes. Second observation which underlies our second Quack variant, which we call the 2x2 method. The observation is that, for instance, we know the set TP union FN. The union of the true positives and the false negatives is essentially the set of items which have been assigned the positive class by the classifier. So it's the predicted positives. And we know the predicted positives. And we know the predicted negatives, Tn, UFP. So in a sense, we can essentially factorize our method. We can generate a method which, instead of training one single quantifier, which has to deal with 4 classes, we train 2 quantifiers which deal with 2 classes each. So one that discriminates between the classes TP and FN, and one that discriminates between the classes Tn and FP. This idea sounds really advantageous, you know, over the 1x4 method for 2 main reasons. Okay, first of all, it exploits additional knowledge, our knowledge of the sets TP union FN and Tn union FP. And also, the second reason is that it implements a sort of a divide et impera principle. So it basically subdivides a complex problem, okay, quantifying on 4 classes, into simpler problems. So quantifying between 2 classes each. Again, this method admits of an obvious multi-class version, which we call the n by n method, since it has to do with essentially generating n quantifiers, each tasked with estimating the class prevalence values of n classes each. There is a third variant, which starts from another observation. And it is the observations that the false positives and the false negatives tend to lie in two regions which are contiguous. Okay, so take the false positives. False positives essentially lie in the region that the classifier has assigned to the positives. Okay, but they probably lie just off the separating surface. Okay, so in a region which is close to the separating surface. Again, this is the same for the false negatives. False negatives lie in the region that the classifier has assigned to the negatives, but the line, most of them lie just, off the separating surface. So these two regions, the region of the false positives and the false negatives, they are, in a sense, contiguous. So, in a sense, we might try to view them as a single region, the region of FP union Fn. So this is the idea on which the 1/3 method is based. Okay, so here, in the 1/3 method, we train on our validation data a single quantifier that has to do with three classes, okay, discriminating between TP, Tn, and the union of FP UN. Okay. So does this work? Well, there's a caveat here. Okay, so this 1/3 method can be used only for classifier accuracy measures that do not differentiate between false positives and false negatives. Luckily, it can be used, say, for vanilla accuracy, because in vanilla accuracy, you can, if you know the, let's say, how many mistakes you've done, okay? So if you know the cardinality of PUFN, it's enough for you to compute vanilla accuracy. And the same for F1. But of course, it's not enough if your classifier accuracy measure is, say, cost sensitive. In cost sensitive classifier accuracy measure, typically, you impose a different cost for a false positive and a different cost for a false negative. So you cannot confuse false positives and false negatives. The two previous methods, instead, 2x2 and 1x4, can be used for all classifier accuracy measure. Say, independently of which of the three variants you can use, something you might want to do is to add new covariates. Add the new covariates to extended representation that, in a sense, make explicit some information which is already implicitly present in the vector. And indeed, we add some covariates that have to do with the, let's say, with the level of confidence with which the classifier has taken its decision. So, for instance, maxconf is one additional covariate. It's the maximum of the posterior probabilities for item X. Okay, so when this is very high, it means that, the classifier has taken that decision with high confidence, and vice versa. Negative entropy is again a different way of, estimating the confidence with which the classifier has taken a certain decision. Okay, so for instance, when entropy is maximum, it means that confidence is minimum. When entropy is minimum, which means, say, one of the posteriors is 1 and all of the others are 0, then the confidence is maximum. And max inverse of max is a similar concept. So we add these additional covariates to the extended representations. Now, let me show you a few experiments, okay, which we have used in order to assess this method. This also gives me an opportunity to look at the type of experimentation that one needs to do when testing systems for classifier accuracy prediction. And here the experiments we have done are aimed at simulating prior probability shift. And they do it by using the so-called artificial prevalence protocol. The artificial prevalence protocol is a method to extract from a given data set, omega, a number of scenarios, to which you can submit your system. Okay? So it's sort of meant to be a sort of a stress test for robustness to prior probability shift, because it simulates a very wide amount of different scenarios, a wide variety of amounts of training data imbalance, of test data imbalance, and a wide variety of amounts of prior probability shift. So the idea is that the artificial prevalence protocol is a way of extracting from a dataset omega a number of training samples, a number of validation samples, a number of test samples, which are characterized by predefined class frequencies. So class frequencies lying on a pre-specified grid. So for instance, you might want to extract a training sample that has only 10% of positives, and ask it to classify a test sample which has 90% of positives. So it means that you have generated a situation with very high prior probability shift. So by experimenting on an entire range of values of this grid, you generate many different situations in which you test your system. So in a sense, this experimentation is a robust experimentation, a stress test for robustness to prior probability shift. Kind of experiments that we run used two different quantification methods, SLD and KDE. These are, I will not enter the details of these systems. It suffices to know that SLD and KDE are the state-of-the-art systems for multi-class quantification method once it has to address prior probability shift. So it is important that these quantification methods are multi-class because, two of our three variants, the 1x3 and 1x4, deal with more than two classes, 3 classes or 4 classes. So we cannot just have binary quantification methods. So this is sort of a table that summarizes a bit our experimental setup. We used 4 very large textual datasets, IMDb, which is, let's say, movie reviews, CCAT, GCAT, MCAT, which are essentially news from the Reuters corpus volume 1. So it's newswire reports. Classifier, we use the logistic regression because logistic regression tends to work very well with text. It's also computationally efficient, so it allowed us to run a large number of experiments. And for quantifiers, we used SLD and KDE. As I said, they are the two state-of-the-art methods. And we also used the trivial classify and count. And the reason why we test the classify and count will be apparent in a while. Concerning the training data, validation data, and unlabeled data, essentially we extract samples according to the artificial prevalence protocol. So, training data, which are needed for training the classifier H, we select training samples, which we extract according to a grid of class frequencies from 0.10 to 0.90, And validation, the validation data, validation samples are needed for training our quantifier. And the validation samples, again, we extracted according to the same 9-point grid class frequencies. So every time there is a training sample, we pair it with the validation sample of the same frequency in order to represent the fact that T and V come from the same data distribution. Concerning the unlabeled data, we extract again test samples according to a larger grid, 21-point grid. This includes also zero prevalence, zero frequency, or 1.0 frequency, because these can potentially happen in test data. And here for each of these class frequency values on the grid, we take 100 random samples per frequency of 1,000 data points each. I will also mention what the baseline systems were we used. Essentially, we tried to use all of the classifier actually prediction methods which have been published in the last 5 years that make their code available, so as not to have to re-implement everything, possibly making mistakes. In terms of classifier accuracy measure, we use 2 different ones. This is something novel in the literature because all of the published methods only use vanilla accuracy. We here use 2, but we could have used many more. And in terms of the classifier accuracy prediction error measure, we use simply the absolute difference between the predicted accuracy and the true accuracy. So I will sort of skip the optimization part. You know, it's the kind of hyperparameter optimization part that you imagine. It's only important to say one thing, okay? So we individually optimized all three variants of our method, one by 4, 2 by 2, 1 by 3, because in preliminary experiments, we had found out that each of them has its own merits. There is none of them which is clearly superior to the other two. So we decided to train the three of them, all of them, and put model selection in charge of choosing the best one according to the given situation. So let me present a few experimental results. Here you are seeing the results for vanilla accuracy as our classifier accuracy measure. On the lines, you have all of the different methods where the baselines are on top and our QUAC variants are at the bottom. And the last row, in this table, essentially boldface as usual represents the best result. And what you can notice is that the best results is always obtained by one of our variant, by a QUAC variant, sometimes instantiated with the SLD quantifier, sometimes instantiated with the KDE quantifier. The next table is the same. The difference is that F1 is the classifier accuracy measure, and instead of vanilla accuracy, which was the case in the previous table. Something to notice, okay, so QUAC is always the winning method. It's always in boldface, as you can see. What we can notice is that it's not always the same variant, okay? So sometimes the KDE variant is the best, sometimes the SLD is the best. It has to be noticed that also the baselines, okay? So it's not always the case that the best baseline is the same. Sometimes it's the DOC method, sometimes it's the ATC method, while the other ones never come out on top. Just for your reference, the baseline, which is here called naive, is what we might do naively, for estimating classifier accuracy on auto-distribution data. Essentially, we test our classifier on our validation set, which is, still coming from the same distribution. And we assume that the same accuracy that we have obtained will also be the case on auto-distribution data. A naive assumption, but we actually tested the effect of this naive assumption. So something else that we should note, is something interesting. Okay, so we also instantiated QUAC with classifying count, with the naive, the most naive of quantifiers. Okay, the result is sort of interesting because in 4 combinations out of 8, we have 4 combinations, 4 data sets by 2 classifier accuracy measures. In 4 combinations out of 8, even QUAC instantiated with CC outperforms the best baseline. Okay, so this is an indication. It's an indication that actually viewing the cells of the contingency table as classes is a good idea. The very fact that the QUAC instantiated with genuine quantifiers, SLD and KDE, always outperforms both QUAC CC and the baselines, is instead an indication that using quantification methods which are robust to prior probability shift is also a good idea. So in a sense, the success of QUAC SLD and QUAC KDE is the result of 2 interesting observations, 2 interesting ideas. Viewing the contingency table cells as classes and using quantification methods which are known to be robust to prior probability shift in order to estimate their frequencies. Something which should be also observed is that the error reduction levels are quite hefty. Okay, error reduction, the last row, indicates the improvement of the best QAC variant with respect to the best baseline. So you might notice that these improvements are quite hefty, ranging from 5% to 31% in the case of vanilla accuracy, but they are even much bigger for F1. They range between 67% to 75% in the case of F1. And this is also an indication that QAC is fairly robust to, let's say, difficult measures such as F1. F1 is a difficult measure because it's discontinuous in many cases. You know, it has a number of formal properties that are not terribly good, you know. So F1 is understandably a measure which is difficult to deal with, you know. And QAC, you might notice that the results of QAC are better for vanilla accuracy than for F1, but the results of the baselines are much better for vanilla accuracy than for F1. So for F1, some of the baselines really perform disastrously. Let's say that QAC is still fairly robust to F1 too, you know. Something that I want to note is that each figure in this cell is the average value of the error measure, the classifier accuracy prediction error measure across something like 18,000, more than 18,000 cases, okay, which result from 9 different values on the training grid, 21 different values on the testing grid, and 100 testing samples for each of the 21 cases, you know. So graphically, you know, this is an example of, let's say, the prediction error, you know, when vanilla accuracy is our classifier accuracy measure on the IMDb dataset. IMDb is a dataset on which we have good improvements with respect to the baselines, not the best improvements. So it's an average for us. It's an average result. So it's the one where we have the lowest improvements for F1. Still, you know, you can see the difference between the baselines and our methods. Our methods, which are green and yellow, you know, the error tends to be pretty stable independently of the amount of prior probability shift, which is indicated on the x-axis, you know. Instead, on the baselines, especially ATC, this error increases a lot when prior probability shift increases. So this is a different plot. So this is F1. It's not vanilla accuracy. It's still IMDb. And instead, the plot is error, classifier accuracy prediction error as a function of test prevalence. Okay, so let's say the proportion of positives and negatives in the test data. Again, you can see that the baselines, blue and red, are much higher than yellow and green, which are our 2 variants. It's quite interesting to see diagonal plots, you know. A diagonal plot is a plot where each, say, blue dot is an experiment in which let's say, the system should have predicted a certain level of accuracy, which is on the x-axis, and instead estimated a different level of accuracy, which is on the y-axis. And because of this, you can notice that the perfect prediction system would have all of its dots on the diagonal. You know, the fact that here we are seeing the naive system. The naive system is really naive, okay, because it keeps predicting it predicts the accuracy that it recorded on the validation data for all samples in the unlabeled data. So it naively assumes that whatever sample you get in the unlabeled data, you will obtain the performance that has been recorded on the validation data. The validation data is recorded quite high accuracy, around 90%, and it keeps predicting 90%, even if it should have predicted 20% or 40% or 60%. So it's truly a naive system. So here is RCA. It's one of our baseline. It's not as naive as the naive system, but it's still, you know, it's far from having all of its points close to the diagonal. Here it's a much better baseline, ATC, you know. You can see that, you know, all the points tend to be closer to the diagonal, you know, although ATC tends to be fairly optimistic. It often tends to predict an accuracy level which is higher than it should have predicted. DOC, another baseline, even better, you know. So here we are seeing a system which tends to approach, you know, the diagonal much more. Our systems are represented like this. This is Quack instantiated with classifying count, the naive system, you know. Still, it delivers reasonably good accuracy, even if no true quantification system is involved. Let's see what the accuracy with involving quantification systems is. So this is Quack instantiated with the SLD, one of the two state-of-the-art quantification systems that we have seen. You clearly see that the performance is the best of the ones we have seen up to now. This is Quack instantiated with KDE, so it's yet another state-of-the-art quantification system, still very good. Sometimes it has some outliers, you know, and we haven't yet figured out why, you know, we are sort of trying to study why there is no these outliers. So this sort of ends my lecture, you know. So what are the lessons learned? Lessons learned about Quack, lessons learned about classifier accuracy prediction. Let me discuss Quack a bit. So we have seen that it outperforms the baselines, that it's robust to difficult accuracy measures, such as F1. And we have seen that even the simplistic Quack gives good results. So in other words, we have seen that the success of Quack comes from two reasons: viewing continuously stable cells as classes and using PPS robust quantification algorithms for predicting the values of these cells. So what can we say about CAP, classifier accuracy prediction? Classifier accuracy prediction under PPS, we have shown that can be performed reasonably well. It's good news. So in our tables, we witnessed average classifier accuracy prediction errors, which are smaller than 2% for vanilla accuracy, smaller than 3% for F1. So 2% means essentially, you know, the true accuracy that I should have predicted is 42%, but I predicted 40% or 44%, you know, reasonably good if we consider that in that protocol, we have subjected our systems with radically large, you know, amounts of prior probability shift. There are still margins of improvement, you know. I also had the slides with the future work that we want to carry out, but I'll skip the slides in the interest of questions. So I'll leave the floor to questions if there are any. And I thank you for your interest.
Thank you very much, Fabrizio, for your very interesting talk. Other questions, please? If there are questions, do raise your voice rather than write in chat.
Hi, can you hear me?
Please speak louder.
Hi, can you hear me?
Yes,
Yes.
we can hear you.
Okay, great. So, thanks. First of all, thank you for this interesting talk. I learned a lot. So I have one first question, which is, I saw that actually the validation set and the unlabeled test set are actually not from the same distribution. So do you have any insight why the quantification method still can train a robust quantifier for this prediction task? Or if that works, can we actually use that technique to train a robust classifier instead, rather than using an additional quantification method to predict its performance? So this is my first question.
It's a very good question. So as you said, you know, the validation set and the unlabeled set come from two different distributions. Okay, and so you were wondering how come, given these different distributions, we can still train good quantifiers, good quality quantifiers.
Yes.
So I would say that the reason is that, you know, quantification as a discipline, as a task, was born with data set shift in mind, with prior probability shift in mind. Okay, so the techniques which are now state of the art are techniques that can bridge this gap, the gap between these two distributions. Okay, so in a sense, so for instance, take SLD. SLD is a method. It's a fairly old method. Okay, it's been in existence for 20 years or more. You know, it's a method that tries to, let's say, update the posterior probabilities, you know, returned by the classifier by detecting a mismatch between the sum of the posterior probabilities and the estimated priors. So it uses expectation maximization in order to iteratively refine both, you know, both the posterior probabilities and the class prevalence values until the two become mutually consistent. Okay, so it's one of the many techniques which have been used, you know, to estimate class frequencies in the presence of prior probability shift. So the second part of your question is, given that we are so good, you know, at bridging, you know, the difference between the two distributions for quantification, can we do it for classification too? Well, yes, you know, this is the task of domain adaptation, you know, and indeed, this technique that I mentioned, SLD, you know, was detected with domain adaptation in mind. So the idea was, you know, to estimate the class frequencies in order to be able to adapt the posterior probabilities to the new reality. Okay, so in order to adapt the classifier to changing conditions. You know? So a lot of the literature in quantification was born out of the desire to adapt a classifier trained on a certain distribution to data on another distribution. So I hope this answers your question.
Okay, thank you. I have multiple questions follow up. So my second question is, what's the link between quark and there are also many works on model calibration, which trying to calibrate the model conference to match the accuracy. Is there any link between the two?
A link between calibration and
the quark.
And quark. Okay, so what is the relationship between? Well, I would say that you know, calibration plays a very important role in quantification, and so it plays a very important role in quark because quark is heavily based on quantification. So just to give you an idea, the SLD method that I discussed, you know, it's a state-of-the-art quantification method. You know, it's a method that tries to update, you know, posterior probabilities. So, so the idea is that it assumes, you know, that the original posterior probabilities are calibrated, but posterior probabilities cannot be, if they are calibrated on a certain distribution, they cannot be calibrated at the same time for a different distribution, you know? So in a sense, you might take SLD, which is a quantification method, a domain adaptation method, as we might call it. You might take it as a means to recalibrate the recalibrate the posterior probabilities for out-of-distribution data. Okay, so to generate posterior probabilities, on out-of-distribution data that, are more calibrated than before, Although, let's say, the task of doing calibration for out-of-distribution data is still, an open problem, and the SLD makes one step towards it.
I see. My third question is about more about the
excuse me for a moment. Let's check if there are other questions by others.
Okay.
Okay, please go ahead for your third question.
My third question is, so I noticed that in the experimental result part, you use multiple different combinations of case from validation and test set. It's kind of like a very huge amount of computing. So I wonder, to deploy Quark, do we need to still following the same regimen?
Maybe I have not entirely understood your question. Let me try to rephrase. You said, I think you said, I have noticed that in order to run Quark, you need to do quite a lot of hyperparameter validation. So
not about the hyperparameter. It's more about the result part. Can you go back to the result slides?
Okay, let me go back to the results. Just a moment. Okay.
Yeah, here. So there is a note in the bottom of this slide. You're saying
Yes.
that you needed to have like more than 18K combinations of training sample and test sample. So I wonder whether in particular we also need to run multiple combinations to get a reliable number, or this is just for the evaluation of the Quark and the different settings.
Essentially, this very high number is for evaluation purposes. Okay, so you, in order to get, let's say, experimental results which are, statistically robust, you want to run many different combinations. Okay, and so many different combinations means that we took, say, 9. Let me go back to. Okay, here. So for training the system, okay, so essentially we don't have a single training set. We have a sort of a pool of data from which we extract training sets. But say one time we extract a training set that has only 10% of positives. Another time we extract a training set which has 20% of positives. Okay, 30% of positives, 90% of positives. So we use a 9-point grid of class frequencies. So for testing, okay, again, we work on a grid. We extract a sample which has, say, 0% positive, or 0.10% positive, 0.20. So you might, there are cases in which you confront, let's say, you use a training set which has 10% positives and a test sample which has 10% positives. In this case, you have no PPS, but you have a case in which you have 10% positives and in the 10% training positives and 90% test positives. So you have an enormous amount of prior probability shift. So in a sense, we generate many different scenarios. Okay, so as I said here, each cell, is the result of testing 18,900 different scenarios characterized by different values of training proportions, testing proportions, and prior probability shift values. Okay, so at the same time, you test situations characterized by training set imbalance, by test set imbalance, and by prior probability shift. So it's hard to, so devise an experimentation which is more robust than this.
I see. That's very impressive. I have one last question, but I saw people also posted in the chat, so maybe I will save my question the other.
Yes.
May I request you send to Professor Sebastiani an email with your question? Typically, a person has one or two questions, not really four in each lecture. Fabrizio, I have a question regarding the use of your work in the following context. Let's suppose that
the use of my what?
Of your work in teacher-student DNN framework. So let's suppose that you have a number of DNNs that have been trained for a certain task on different types of data. Then you get a test data set, you check your own DNN, whether it performs well or whether it has good accuracy. If it does not have good accuracy, it is already problem number one, how to assess this. Then you send these test data sets to the various teachers and you choose the one that has best performance. We have addressed this issue by using out-of-distribution detectors, which is a slightly different methodology. Do you think that your technique can be used in such a setting to choose the best teacher?
I would have to think about it. Maybe it's you are catching
we have worked in this domain, so maybe this could be a possibility for cooperation, also the framework of the AI for Media project.
Yes, I agree. We should well, the question catches me a bit off guard, and I should maybe think about it, and maybe we should talk about it offline because it's
sure. It could be a good application of your work because we solved such problems in an indirect way, not in a direct way.
Yes.
But there can be an alternative to this. Is there any other question? If there are no other questions, then I would like to thank.
Can I answer the fourth question by Chen? Because I saw it in the chat and I noticed it's an interesting question.
Okay, please go ahead.
So the question is.
Thank you. I was about to say it.
Yes. I saw that the question is, can Quark be applied to predicting the errors of regression problem? Okay, so the question, I guess, is, can Quark be applied to predicting the accuracy of a regressor instead of a quantifier? I had never really thought about it, but what I can say is that what comes to mind is the fact that, in quantification, so there is something called regression quantification. It's something that stands to regression as standard quantification stands to classification. Okay, so maybe, I don't know, by looking at techniques of regression quantification, one might try to predict the accuracy of regressors on out-of-distribution data. But this is very much a maybe because I have never really, asked myself this question. And thank you for asking this.
Yeah, because I feel like there is not so much work on the regression problem, but it can be very important because I'm working in healthcare. So sometimes the task is about the regression, and
you work in what?
I'm working on healthcare application.
Healthcare, yes.
Yeah, I'm also working on some other domain prediction, etc. But I saw that currently there is not too much work on the regression tasks where the output is less bounded compared to the classification.
Yes. That's very interesting. Let's talk about it further, maybe offline.
Yeah.
But it's you posed an interesting question and might be an interesting research problem which might have solutions.
Cool. Thank you. Thank you for your time.
Thank you.
Is there any last question, please? Then I would like to thank you very much, Professor Sebastiani, for his very interesting talk, and I would like to thank all of you for participating. Please keep tuned for future AIDA AI lectures. Thank you again. Bye.
Thank you very much. Thank you all.
Maybe it's time now to start.
Great.